Welcome to the Explainer. Today, we're investigating a brand new way to stop AI models from getting stuck in those repetitive reasoning ruts we've all seen. We'll be exploring a method called exploratory sampling. We all know large language models are incredibly powerful, right? But getting them to genuinely brainstorm, to give us truly different approaches to a problem instead of just regurgitating the exact same answer with different synonyms, well, that remains a massive challenge. So today, we're unpacking a fascinating piece of research that proposes a really brilliant solution to this exact problem.
Here's our roadmap for the explainer. We'll start with 1, the diversity problem. Then 2, surface versus semantic variation. 3, enter exploratory sampling. 4, the latent distiller. 5, novelty as a signal. And finally, 6, the performance boost. We're going to take a structured journey straight into the engine room of LLMs to see how we can move them from surface-level repetition to actual genuine semantic exploration. Let's get right into it. Section 1. The diversity problem. Let's establish exactly why AI gets stuck.
Okay, so have you ever noticed that when you ask an AI to generate a batch of candidate solutions, it kind of just repeats the identical core logic over and over? It leads to these highly redundant, basically useless answers. In the AI world, this is a major hurdle for what we call test time scaling, which is essentially just giving the AI more time to generate and evaluate multiple answers before handing us a final response. When we want an AI to solve a complex math or coding problem, we usually ask it to generate multiple potential solutions, and then we try to pick the best one. But if the model has a systematic failure pattern, or if it's just fundamentally stuck on one single way of approaching the problem, generating 100 variations of that exact same flawed logic doesn't help us at all. The subsequent selection mechanisms literally cannot pick a correct solution if there isn't one in the candidate pool to begin with.
Which brings us to Section 2, surface versus semantic variation. Or, as I like to think of it, the difference between just changing the garnish on a dish versus actually changing the recipe.
On one side of the spectrum, standard stochastic sampling methods like top P or min P inject randomness by truncating the probability distribution and picking different words. But, as the researchers point out, this really just induces surface-level lexical variation. It's entirely syntactic. It changes how the answer is written, sure, but definitely not how the problem is solved. Now, on the flip side, we have structured search algorithms like Tree of Thoughts. These explicitly branch out and traverse completely different reasoning paths. And they're great at finding high-quality, diverse semantic trajectories. But the catch? They are incredibly slow. Their reliance on explicit branching and backtracking makes them completely impractical for high-throughput, real-world generation tasks.
That specific trade-off sets the perfect stage for our source material's proposed solution. Section 3. Enter exploratory sampling, a totally new decoding approach.
So here is the absolute game changer. Exploratory sampling, or ESamp, actively steers the AI toward less explored semantic regions rather than just making superficial syntactic changes. And it does this by operating not just on the vocabulary level, but deep down within the continuous representation space of the model itself. When the model is generating text, ESamp is looking at the underlying meaning, the latent representation of the context. If the model is about to spit out a token that perfectly aligns with a reasoning pattern it's already used in parallel generations, ESamp explicitly penalizes it. It basically forces the model to pivot and explore genuinely novel solution strategies instead of just rewarding its previous failed attempts. So how exactly does it achieve this semantic shift? Section 4, the latent distiller. This is all about predicting the AI's internal thoughts. Think of this latent distiller as a tiny, lightweight traffic controller placed right inside the model, continually learning the AI's depth-wise representation transitions on the fly. It's a small, multi-layer perceptron neural network living inside the massive large language model. And what it does is honestly brilliant. As the AI generates text, the latent distiller peeks at the shallow layers, the very early stages of the AI's internal processing, and it tries to predict what the final deep layers are going to output. And it's doing all of this online, at test time. That means it is constantly adapting and learning the current context while the AI is actively working on your specific prompt.
The mechanics here are super elegant. The hidden state moves directly from the first transformer layer right into the distiller block. The distiller grabs that context-aware representation from layer 1 and immediately tries to predict the output of the final transformer layer. It then projects this prediction through the language modeling head to get its own set of vocabulary probabilities, what we call distilled logits. Finally, there's a mixing step where these predicted probabilities are combined with the actual probabilities generated by the full heavy lifting of the entire transformer stack. This whole setup is the key to measuring predictability.
This leads us right into Section 5,
Novelty as a signal. Let's talk about the power of the surprise heuristic.
ESamp leverages a pretty fundamental property of neural networks here. If the model accurately predicts its own deep layers, it's essentially bored and just repeating itself. But a high prediction error, that means it's surprised and it's exploring new semantic territory. This concept is actually grounded in something called random network distillation. Think about it for a second. If the latent distiller can easily predict the deep layer's output based solely on the early layer, it means the model is traversing a highly familiar internal pathway. It's doing exactly what it just did a second ago. That's redundancy. But if the distiller's prediction is way off, a huge prediction error, it indicates a massive deviation in the representation space. The model is exploring a totally novel semantic configuration. It's surprised.
So let's walk through how this builds into a clear four-step sequence. First, the distiller predicts. Second, it compares the error. Third, it assigns a novelty reward for that surprise. And finally, it reweights the tokens so the AI actually chooses the less explored path. This step-by-step process is really where the magic happens. By calculating the error between the latent distiller's shortcut prediction and the full model's actual deep layer, ESamp figures out an intrinsic reward. It then takes that reward and modifies the final probability of the next word. It actively suppresses the probability on redundant continuations, steering the whole generation process away from the familiar and pushing it hard toward underexplored reasoning patterns.
Now you might be wondering, how do we keep the AI from going completely off the rails? Well, this process is anchored in a KL-regularized optimization objective. You can think of this as a mathematical leash. It ensures that while the AI is strongly incentivized to explore novel semantic regions, it still absolutely has to generate coherent, valid text that respects the foundational training of the base model. It strikes this perfect balance between seeking out novelty and maintaining high generation quality, so you don't just get pure gibberish just for the sake of the model being mathematically surprising.
Section 6. The performance boost. Better reasoning, lower overhead. We've gone through the math, but does forcing all this surprise actually result in smarter outputs in the real world?
Yes, it does, and incredibly efficiently. Because the distiller trains using an asynchronous pipeline decoupled from main generation, ESamp creates less than a 5% worst-case latency overhead in standard serving scenarios. Remember earlier when we talked about how structured search methods like Tree of Thoughts were just way too slow? Well, this is the researchers' answer to that. They built a high-efficiency asynchronous pipeline. The training of the latent distiller and its inference actually happen alongside the main LLM generation without blocking it. In fact, their optimized open-source release gets that overhead down to just 1.2%. That makes genuine semantic exploration totally practical for large-scale, high-throughput deployment.
And the results are seriously striking. It powerfully boosts PASCAC efficiency by finding correct answers with far fewer tries, and generalizes beautifully across difficult math, science, and coding benchmarks. By the way, PASCAC is just a metric measuring whether the correct answer is found within K-generated attempts. Because ESamp ensures every single attempt is semantically distinct, you don't need to generate 100 answers to find a good one. You can generate far fewer, saving immense computational resources. Standard heuristic methods usually ruin a model's ability to code or do math because they blindly force different vocabulary. But ESamp's focus on deep representation maintains coherence while skyrocketing creativity. It literally breaks the old trade-off entirely.
So, wrapping up this explainer, we're left with a pretty profound question to chew on. If artificial creativity is just the optimization of prediction errors and semantic novelty, what bounds can we truly push next? By shifting our focus from the surface level of the words being generated all the way down to the internal, latent representations of meaning, exploratory sampling opens up an entirely new frontier. It proves that we can teach our AI models not just to talk differently, but to actively reason differently. Thanks so much for joining me on this deep dive.